Lesson 8.3 is on vectors, operations, and the dot product. And so let's talk about vectors. Vectors is something that students have kind of a hard time understanding. Vectors are going to have two main attributes. Going to have magnitude and direction. Magnitude and direction. So let's think about it from a graphical standpoint. If I told you to graph the point 6, 8, I think you would have no problems graphing 6, 8. You go 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. 0.68. Right there. Okay? But vector notation, it's going to look like this. And so it still uses that 0.68, but we're going to draw an arrow from the origin up to that point and make sure to stop. So that looks like the vector 6, 8. Now one thing to watch out for. Sometimes people will think about geometry and think about array. And array is a little bit different. Okay? They'll start here and they'll give the right direction, but then they'll go right through that point and then just go like that. Okay? That's not the same thing as a vector because that messes up the magnitude. If a vector has magnitude and direction, we got the direction right, but we got the magnitude wrong. Think about a football player, okay? And here's the quarterback, and the quarterback's going to throw to a receiver, and the receiver is located at the 0.68. Quarterback throws a pass from his position to the receiver's position. That's going to look like this vector, as shown. But if you draw this vector like this, that's an incomplete pass because he doesn't hit the receiver. He throws it over his head or something. Okay? So make sure you understand that vector is going to stop at that point. It has magnitude and direction. Now, what we're going to do at some point, and we've done this a lot this semester, but we're going to end up making a right triangle, and we will need to use SOHCAHTOA to figure out things like this angle right here, or the magnitude of this side over here, the hypotenuse, or we might need to find this length, this side length, or this side length. We're going to use basically SOHCAHTOA to figure out those different parts of that triangle based off of that vector. So let's talk about some terms. The scalar is talking about the magnitude of a quantity. And that's the size, or the number, the value. A vector in the plane is a directed line segment. Okay, think about like a ray. Okay, but a ray goes on forever. This won't go on forever. So we can write it as this bold OP like this. Ray OP, here's O, and here's P. Or you remember we wrote it like that in geometry, that meant array. When we're talking about vectors, keep in mind the magnitude. O is the initial point, P is the terminal point. And so then the magnitude, or the length of the vector, is expressed, looks like it's in absolute value bars. So we read that as the magnitude of vector OP. Two vectors are equal if and only if they have the same magnitude and the same direction. So there are those two words again, magnitude and direction. You can see vector OP and vector PO are not the same because they have different directions. Vector A equals vector B because they have the exact same magnitude and direction. But when we look over here at vector E can't be the same thing as A because they've got different directions. And then obviously vector F isn't the same size as A, so they have different magnitudes. We're going to need to add two vectors together. So let's think about the sum of two vectors. You're going to have one of two pictures, like this one or like this one. And I call this picture the golf ball problem, and I call this picture over here the dog walker. And it's a little bit harder to understand one than the other, but they're both doing the same thing. They're talking about something called the resultant vector. Okay, so the resultant, so know that word. So the resultant vector is like the sum. And so let's look at this. Okay. A minute ago we graphed the vector 6, 8. So let's just start with that. I'm going to call that vector A. Okay, vector A. And then I'm going to also have another vector 5, negative 2. Okay, so let's also graph the vector 5, negative 2. 1, 2, 3, 4, 5. 1, 2. Just think about the point 5, negative 2. And I'll call that vector B. Okay? So, I want to add those two vectors together. Okay? There's two different ways I can do it. There's either the golf ball or the dog walker. So, golf ball or dog walker. The way it's drawn right now, to me, looks like the dog walker problem. Okay, so imagine if somebody is walking two dogs. And one of them is a really big dog, and one of them is a really little dog. Okay? Those two dogs are pulling him. Let's say this guy's on roller skates. Okay, so he's not really applying any extra force, but those two dogs are going to be pulling. And they're going to be pulling kind of, in this direction. The stronger dog or the stronger force is going to be pulling more than the weaker dog or the smaller force. And so it's going to be pulling in that position. Okay, so I call this problem, the way it looks, I call this the dog walker problem. I really struggled with this when I was in school, so make sure you're focused. Okay? If we want to find the resultant, what we're going to have to do is draw a parallelogram. Draw a parallelogram, and the resultant force goes from the starting position to the opposite corner. That's the resultant force. Okay? So that's what we're going to do. Every time we see a dog walker problem, we're going to draw something that looks like that. We have to draw the parallelogram and draw the vector connecting the initial corner to that opposite corner of the parallelogram. Okay? So if I wanted to look at the golf ball problem, let's change it. Let's say we're hitting a golf ball. And so here's a golf ball. And what do you do when you play golf? You line up, you hit it, and it's probably not going to go straight, so it goes over here, okay? And so then you go up and you hit it again, and so what I want to do is I want to hit this vector B, and I'm going to add this vector B onto the end of it, and so what should happen is you should end up, here's your first one, you hit your second one, and it should end up taking you to the same place, if you do your picture right, okay? The resultant vector is going from this start to right here. This is still the resultant. It's the same result. It's the same resulting vector, whether I do the golf ball picture or the dog walker picture. Okay, so just be aware that there are two different ones that you're going to have to look at. So when I look back here, notice this one is the golf ball. Hit the first ball, hit the second ball. Here's your result. It goes from start to finish. I think that's the easier one to understand. But over here, the dog walker problem, you've got two dogs. And those dogs are pulling you this way. There's your result. So when we have to add two vectors, let's say we're doing B and C. Okay? So here's vector B. And here's vector C. If I just have to add two vectors, I'm going to call this. Is this golf ball or dog walker? This is dog walker. Okay. Dog walker, you're going to have to draw the parallelogram. And the resultant force is there. Okay. It's going to be a little bit closer, skewed towards the stronger force, but there it is. Okay. But now, if I wanted to draw B minus C, okay, B minus C is a little bit different, it's a little bit harder to understand. It's harder to understand subtraction. So what I'm going to do is add the opposite. And so I'll treat it like an addition. B plus the opposite of C. And so what I would do then is take this C and draw its opposite force. And so I would find the resultant of B and the opposite of C. And so here's B, and here's the opposite of C. I would draw that parallelogram. And the resultant force of that would be right there. It's still a dot blocker, but that's how you would do B minus C. So this slide on a scalar product of a number, it's just saying you can multiply a vector times a number, it'll change its length, it'll change its magnitude. If you multiply times a negative, it's going to change its direction. A vector with initial point at the origin is called a position vector. And a position vector with endpoint at the point AB is going to be written in this form. And so we've already seen one. It might have been 6, 8, and that just means that that vector ends or terminates at 6, 8. They're going to ask you some questions about horizontal and vertical components. Just understand that when they talk about horizontal components, they're talking about the x number, and when they talk about vertical components, they're talking about the y number. That's going to be big. Also, when you end up having to find angle theta, it's going to have to be a positive number. There's going to be a calculator question where your answer comes out of the calculator and it's going to be a negative angle. But just understand you're going to have to think about where that is on the plane and make it a positive angle based on what quadrant it's in. Magnitude and direction angle of a vector. We're talking about a vector u, and if we want to calculate the magnitude or the size, it's going to be given by this formula. Magnitude of u equals square root of a squared plus b squared. Now that's supposed to look like Pythagorean theorem, and that's what we're doing. We're basically finding the length of the hypotenuse. Direction angle theta is going to satisfy the formula tangent theta equals b over a. So notice your AB points are like x and y. So really we already know both of these formulas. If you think back to chapter 5, we had tangent theta equals y over x, and that's exactly what this is. Tangent theta equals b over a is the same thing as tangent theta equals y over x. We've already done that. We've already used both of these formulas. So these are formulas for finding magnitude and direction of a vector. Example 1 says find the magnitude and direction for this vector 3, negative 2. I think we probably need to draw it. Let's draw it and look at what it is. The point 3, negative 2 takes us right here. So look at the vector. The vector is going to take us in that direction up until that point. Let's make that into a right triangle and do what we've done so many times this semester. I know this side is 3 and this side is 2. I'm going to call it negative 2 just to keep track of my signs. But in order to find the magnitude, I'm going to use this formula. Magnitude u equals square root of, got 3 squared plus negative 2 squared. Magnitude u equals square root of 9 plus 4, or square root of 13. So my magnitude, or my size of the vector, the length of that vector, is the square root of 13, and that's about 3.6 or so, I don't know. So we have to find the magnitude and the direction angle. We can pretty easily, using SOHCAHTOA, find that angle theta right there. We know tangent theta equals y over x. So we've got tangent theta equals negative 2/3, and in order to solve that, we're going to do an inverse tangent and use our calculator. Inverse tangent, negative 2/3, gives us kind of a weird result, the negative 33.7. Okay, now remember, you might remember back from a slide a slide before that we're not allowed to have a negative angle. That answer has to be a positive. So this should kind of make you think, hey, maybe something's not right. But just remember, that's a reference angle. Really what that means is 33.7 where tangent is negative. But that's okay because we're in quadrant 4, and that's one of the places where tangent is negative. It's a 33.7 degree reference angle in that 4th quadrant. And so think about what we've done so many times before. In order to find that angle in the 4th quadrant, we're going to take 360 minus that reference, 33.7. 360 minus 33.7 is 326.3. Theta equals 326.3 degrees. So now we have a vector with magnitude square root of 13 and direction angle 326.3 degrees. Next, we're finding horizontal and vertical components. Keep in mind, horizontal is talking about x, vertical is talking about y. So when we have a vector with magnitude u and direction angle theta, we can find those horizontal and vertical components. Okay? The horizontal component, or the x component, is going to be magnitude u times cosine theta. So remember back all the times throughout the semester where I've said x goes with cosine, x goes with cosine. And y goes with sine. And so we've got formulas for finding the horizontal and the vertical components, or the x and the y. Because you're going to have a vector that's written in xy form, basically. That's usually what's going to happen. Okay? So example 2 says vector w has magnitude 25 and direction angle 41.7. Find the horizontal and vertical components. Horizontal is talking about x. So we can find that by saying the magnitude times cosine 41.7 degrees. Calculator, need a calculator, make sure it's in degrees. 25 cosine 41.7 is about 18.7. We also had to find the vertical component. Remember, the vertical component is the y, so we want y equals magnitude times sine theta. $16.6. So there we just found the horizontal and the vertical component. Now sometimes it might ask you to put it in vertex or in a vector form. So you might have to write it as a vector, and so it might look something like this. But that's the same thing. You've got your horizontal and your vertical right there. So in example 3, we're doing basically the same thing. It says write each vector in the figure in the form AB. So they want vector form. Keep in mind they're talking about x and y. So they're asking you for the horizontal and vertical components. I see 3 different vectors. Let's look at vector u, which is the blue one first. Notice that vector has magnitude 5 and direction angle 60 degrees. Okay, that's important. You've got magnitude 5 and a direction angle 60 degrees. So vector u would equal, okay, let's look at the x component. It's going to be magnitude times cosine of the angle. And then the y component, or the vertical component, would be 5 times sine of that angle. So we can use a calculator maybe, but those numbers are in the chart, so let's use the chart. Anybody tell me what cosine 60 is? 1/2. And sine 60? Square root of 3/2. So if we if we multiply 5 times those things and put it in fraction form, we would get 5/2, comma 5 squared root of 3/2. There's vector u. Now if you look at vector v is actually going to be kind of easy because it's right on the axis. And so if you're smart, you already know that this is going to be -2, 0. Basically, that point is talking about the end, the terminal point. Okay, right at the end of it. Okay, but if you didn't know that, we can calculate it in the same way. we would do magnitude 2 times cosine of the angle and magnitude 2 times sine of the angle. Cosine 180 is -1, sine 180 is 0. So if you clean that up, 2 times -1 is -2, and 2 times 0 is 0. There's a So then we've got 280, we've got vector W, which is the green one down here, and that's going to be 6 cosine 280, 6 sine 280. And I'm not even going to mess with the chart or whatever, I'm just going to type this in. 6 cosine 280 is a nasty looking decimal. So let's round off to 1.04 for the x component, and 6 sine 280, -5.91 for the y component. On example 4, I purposely blocked out the picture just because I think it's good for us to draw our own. So let's look at what we have. Two forces of 15 and 22 newtons act on a point in the plane, and then the angle between the forces is 100 degrees. So let's draw what that looks like. We've got 15 newtons and 22 newtons. It doesn't have to be perfect, with 100 degrees in between the two angles. That's really all they give us to go by. And they want us to find the magnitude of the resultant vector. So the resultant vector is either going to be a golf ball problem or a dog walker problem. And so you look at this picture, and this looks like the dog walker problem. So I will set up my parallelogram, draw a parallelogram in order to find the resultant force. There it is right there. Now what we've done is we've drawn that resultant right through that 100-degree angle. And so please notice that it's not going to split 50-50. That's not going to be 50 on one side and 50 on the other side, because one of the forces is stronger than the other. So you would expect the resultant force to be closer to the stronger force. So what are we going to do? Well, since this is trigonometry, a lot of the times we're going to have to deal with a triangle, and that's exactly what we want here. Notice that we have actually drawn a triangle inside of our parallelogram. So we're going to go back to the last slide and kind of use some of those properties. And notice in problem number 2, or property number 2, adjacent angles of a parallelogram are supplementary. And that's kind of the big one that we would need here. And so when I look at this parallelogram, I know that this angle right here is 80 degrees. This angle and this angle are supplementary. I know those two angles add up to 180, and that tells me that that missing angle was 80 degrees. That's huge. I also know, because opposite sides are congruent, I know that side is 22. And so if you notice inside your triangle, think about the temple runner. The temple runner is running around here collecting tokens. It looks like he's going to get SAS. We have a triangle with SAS. That points us to law of cosines. It's case 3, law of cosines. And so knowing SAS tells me which formula to use. So with either of the two formulas, law of cosines or law of sines, it's important to establish this partnership. I know that R and that 80 are linked together by the formula. And so the formula is going to look like this. R squared equals 15 squared plus 22 squared minus 2 times 15 times 22 cosine 80 degrees. The most common mistake that people make is they don't find that 80 and they just plug 100 in right there. That's not going to cut it. If you think about what that would find, if you use the 100, it would end up finding this side, and that's not going to be the same thing as the resultant force. If I'm thinking about my dog walker problem, that would be the distance between the two dogs' heads, I guess. And that's not what I'm finding. I'm trying to find the resultant force. So good news is we're just going to plug that into a calculator. Let's see what happens. 15 squared 594.4. We're getting r squared is about 594.39, I guess. I'm not going to write down the whole thing because I'm not finished with r. To find r, I take the square root. And I get about 24.4. 24.4 newtons. Now, before I circle it, I might just look and see if that makes sense. 24.4 newtons. Yeah, I'd say that makes sense. That's the resultant force of 22 newtons and 15 newtons. Answer is 24.4 newtons. So then, before we move on, I just would like to draw another picture. I want you to think about how this picture works. And think about a force of 14 newtons and another force of 18 newtons with a 50-degree angle in between them. So, I don't know. It doesn't have to be perfect. Picture's going to look something like this. So if I was going to find the resultant force, draw your parallelogram, draw that diagonal, there's the resultant force. If I was going to continue, I would need to find this angle is 130. We know that because 50 plus 130 is 180. And I would know this opposite side is 18. I'm just trying to find a triangle, and then the temple runner can tell me what to do from there. That's side angle side. I know that's case 3. I know that's law of cosines. I plug it in my formula and find that resultant. Next, we're going to talk about vector operations, just add, subtract, that kind of thing. And this is one of the easier parts of the lesson. But look at example 5. You've got vector u and vector v. We're going to add them. So really all you do, and you can do this in your head, but just add the parts. Add the x terms, negative 2 plus 4 is 2, and add the y terms, 1 plus 3 is 4. That's all you do. Now when we multiply, maybe it's even easier. We're going to multiply negative 2 times the u vector. And so, I don't know that you need to write this, but I guess you could. It's kind of like distributive property, I suppose, but we're just multiplying each piece of the vector by negative 2. We're going to get negative 2 times negative 2 is positive 4. Negative 2 times 1 is negative 2. Now the last one here is a little bit harder. Sometimes people mess that one up. It's got 2 steps to it, so make sure you do 2 steps. We've got 4u, and so do that in your head. Take that u and multiply it by 4. So 4 times that u is going to be negative 8, 4. And then we're going to do 3v. So take that v and multiply by 3, we've got 12, 9. We're going to subtract those 2 vectors. Okay, so the last step, we'd have to take what we just got and subtract it. So that's fine. Negative 8, subtract your parts. Negative 8 minus 12 is negative 20. 4 minus 9 is negative 5. So we would have the vector negative 20, comma 5. Talk about unit vectors. When we talk about a unit vector, it's going to have a magnitude of 1. Okay, so right here is a unit vector. It has a magnitude of 1, and right here, the unit vector, it has a magnitude of 1. Really, anything along the unit circle. It doesn't have to be at a 90-degree angle. This could be a unit vector because it has a magnitude of 1. So anything that has a magnitude of 1 could be a unit vector. Then they introduced this other terminology, 3i plus 4j is the same thing as 3 comma 4. Okay, it's the same thing. So if I give you a vector 6, 8, you might have to write it as 6i plus 8j. It's just important to notice the x part is 6 and the y part is 8. It's really hard to mess that up, I think. Dot product. Dot product is really important. It's going to tell us some stuff about the angles between 2 vectors. Here's how you calculate it. U dot v. Now you might notice that that symbol looks an awful lot like multiplication, but it's not quite the same thing. Not quite the same symbol as multiplication. Do not say u times v. You're going to say u dot v for the dot product. U dot v equals And so notice over here you've got these two vectors. We're going to dot product those. Really all you do is you multiply those and add them together. So it's going to be AC plus BD. This is a number. Not a vector. It's just going to be a number. And that number is going to tell us something about the angle between two vectors. So example 6. Example 6a, we're going to find this dot product. Really all we have to do is multiply these two. That's 8. And multiply these two. That's negative 3. So 8 plus negative 3 is 5. That's it. That's the dot product. Okay? Now what that tells me, we'll go more into it later maybe, but that number, when it's positive, tell me that it's an acute angle. An acute angle in between the two vectors. So is anybody ahead of me and already done the next one? What did you get? 0. Good. You have 6 times negative 2 is negative 12, plus 4 times 3 is 12. You've got a dot product of 0. Okay? 0. That's an important one. 0 is going to indicate this word called orthogonal. Orthogonal seems like a really tough word, but when it says orthogonal, that means basically we're talking about a 90-degree angle. Okay? There is a 90-degree angle between the two vectors. So we could draw them out, but once we draw them, you're going to see there's a 90-degree angle between the two vectors. A negative dot product would indicate an obtuse angle. But we saw positive was acute, and 0 was orthogonal or 90 degrees, but a negative answer would have been obtuse. Here's a list of properties of the dot product, but probably the best property of the dot product is a formula that allows us to calculate the angle between the two vectors. This formula is cosine theta equals the dot product of the vectors divided by the magnitude of each vector multiplied together. So box that in. That's a big formula that tells you the angle between two vectors, basically. So example 7 says find the angle between those two vectors. So we look at the formula, cosine theta equals the dot product divided by the magnitudes, the product of the magnitudes. And so look at your vectors. Here's u and here's v. We're going to dot product, so multiply those and multiply those. Dot product is going to be 3 times 2 is 6, plus 4 times 1 is 4. We can tell that dot product is going to be 10. That's the easy part. And something to note is that when we get a positive value right there, I already know that the angle between the two vectors is going to be acute. Okay, if that number is positive, the angle is acute. If that number is 0, it's a right angle. And if that number was negative, it'd be an obtuse angle between the two vectors. So right now I know it's acute, but I want to know specifically what it is. So then look at the bottom of this formula. We need to find the magnitudes of the vectors. Remember, the magnitude of a vector is square root of a squared plus b squared. It's just like finding the hypotenuse of a right triangle. But here's a and b for your vector. So for vector u, the magnitude is going to be the square root of 3 squared plus 4 squared. And for magnitude v, we'll do the same thing. It's going to be the square root of 2 squared plus 1 squared. So I have the square root of 9 plus 16 is 25, square root of 25. Square root of 25 is 5. And I have the square root of 4 plus 1, that's the square root of 5. So magnitude of u is 5, and the magnitude of v is the square root of 5. And so if we clean up this formula, I have cosine theta equals 10 over 5 times the square root of 5. Now you might be wondering or thinking that we need to rationalize that, and it doesn't really matter. I suppose it doesn't hurt anything, so let's go ahead and rationalize. It doesn't really matter, though, to rationalize, because in order to find theta, and that's what we want, we're going to have to do an inverse cosine. And the calculator doesn't really care what you plug into the calculator. So theta is going to equal inverse cosine of whatever that was that was plugged in. So whether you rationalize or not, doesn't really matter. Let's do an inverse cosine. What we have is 2 times the square root of 5 divided by 5. Okay? So 26.6, theta is about 26.6 degrees. I'm talking about the angle in between the two vectors. Now remember, we knew that it was going to be acute as soon as we got that dot product value of 10, but specifically, that acute angle is 26.6, about. So this chart kind of sums it up, and it says if that dot product is positive, like the number we just got a positive 10. So if it's positive, we're talking about an acute angle between the vectors. And what I mean by that is, here's vector u, and here's vector v. This angle right here in between them is an acute angle. If the dot product is 0, we call that orthogonal. And that's talking about a right angle, or a 90-degree angle in between the two vectors. So that's like if this is vector u, and this is vector v, and that's a right angle, those two vectors would be orthogonal. And then a negative value, if you would get a negative value for the dot product, that's going to be an obtuse angle. So I've already talked about this, but if the dot product is 0, then that's going to end up making cosine theta equals 0. And you can solve that equation to find a 90-degree angle. We're talking about perpendicular vectors, and that's where this word orthogonal comes in. Orthogonal. Talking about perpendicular vectors.